Recording.
All right. So good morning, everybody. And thank you very much, Sergio and Maziar, for the introduction and also the opportunity to talk to you today. It is my pleasure to basically talk within this webinar series on the various tools, because today I wanted to tell you about the finite elements and specifically how they are particularly appropriate to model material instabilities. So I guess the first thing is to understand how this presentation fits within the webinar series. And for that, I just wanted to tell you about my vision of numerical simulation. And if I had to show you one picture that represents numerical simulations, this would be it. So maybe not what you might have expected, but what I mean by that is that it's all about the layering, right? So just like onions, on the outside, you've got reality with all the details and imperfections. And on the inside, through all the layers, you have basically a simple, simplistic model, I could say. Now, the purpose of numerical simulations is to get towards the reality. And therefore, the outside layer is all about uncertainty quantification. And as we just heard, the next seminar will be given by Florian Wellman, who will tell you all about this. So I will not really touch this. All I will say is that this is an important part, but there are many things below. So as a layer of the onion, we're just going to take that layer, peel it off and put it on the shelf for a second. And therefore, before we run many simulations, let's focus on running one simulation. So for that, the next layer is about the material parameters. You can see from the reality on even on this picture of the skin of the layer of the onions, that's, there's all these different shades of colors, and therefore these are the links to geostatistics. You need to understand the spatial variation of the material parameters, the real measurements, the distribution functions, the imperfections, and all of these things. Very important, but this is one layer that we're going to just peel off, put on the shelf as well. And now from our single simulation that has all these realistic views, we're going to go to a homogeneous material parameters everywhere. So even for that, there is still another layer, which is about the geometrical effects. So if you've played these games of entangled sticks, you all know that for here, the physics is very simple, okay? It's all the same material parameters, all in wood, and it's just the entanglement that makes it tricky that when you touch one side, the other side is moving. So again, to understand what really is happening, we're gonna peel this layer off, put it on the shelf, and now we're back to single simulation, single material homogeneous parameters, single geometry, which the simplest one would be, let's say, a cube or a sphere. And then I hear you wonder, but what is left? Well, what is left is the real core of the onion, and that's the physical model. And this is really where things should start with the choice of the physical processes that you want to model, including the length scales at stake and the time scales you want to consider. So it is all about formulating your system of equations and getting the material response. And the keyword material is because there is no geometry, no material parameters, no uncertainty quantification in there. So that really allows to focus on the driving mechanisms. And this is why we talk about material instabilities. And those material instabilities are quite important in our field because they link to a lot of localization phenomena. So that can be in the shape of faults or fractures, boudinage, landslides, or deposits or formations, which in my world of mineral exploration is particularly important in Australia. So once you think you understand what is the driving mechanism and what might be responsible for some of those material behaviors and material instabilities, then it is time to pick back all the layers of the onion on the shelf, assemble them all back, and go back up the stack, because obviously we do want to use numerical simulations towards uncertainty quantification, as we'll see next time. So in that quest, let's see why it is important to look at those material instabilities. And it's basically because of the extra information it can bring. It's sometimes too easy to jump to a conclusion thinking we do understand the physics enough, let's go straight to running plenty of simulations. And this example is here to explain to you why that could be a problem. So this is a picture from the Vian slide. And in case you don't know, I encourage you to Google it, and you'll see that in 1963, it was a catastrophic event where you can see that half of the mountain basically just went off, fell at the bottom into this lake, triggering an immense wave, jumping some 200 meters above the dam and gushing through the valley and killing some 2,500 people or something. So a real tragedy, and yet people thought they really had understood the basics. So it is all about a hydromechanical problem, so pretty well understood. It's all about pore pressure that diminishes the effective stress, so nothing too hard in there. people were aware of the fault in the mountain and therefore monitoring it. So the idea is that that graph at the top here shows you the precipitations, the amount of rain that's falling. And the idea of a hydroelectric dam is obviously to raise the level to make electricity. So people would, let's in the second graph, raise the level of the dam. And at the same time, there's the third graph in red, monitor the movement of the fault. And as they would see the fault starting moving quite fast, they would then drop the level of the dam. And as the level diminishes, then you can see that the fault stabilizes, the movement stops, it becomes stable again, and people think, okay, we really understand hydromechanics 101. So a little bit, increase again the level of the dam because it's all about the business model, and up to the point where the fault starts moving again. And when the fault accelerates with this pronounced curve on this side here, then it is time for them to just stop and lower the level of the dam. And as you can see, it indeed stabilizes the fault. So second time works like a charm. Let's see if we can get third time lucky. Increase again the level of the dam. And as you see the same sharp increase, people did the same response, which is lower the level of the dam. Unfortunately, for this third time, the fault continued moving. There was no stopping it. And here is the result. So what we learned from such events is that physics that is quite often thought to be really well understood is not necessarily so. And in this particular instance, many models have been shown to really capture pretty well the evolution of the velocity of the fault as a function of time. And then what you get is this hyperbolic response that at a finite time, you've got this blow up, this explosion, this catastrophic event, and many models can capture this. The difference, however, with a material instability approach, in this case, this is some work from a colleague, Multiphysics, looking at putting the thermal component. And it is about a thermal creep model. It gives you the exact same match as everybody else, except for one point, which is the one on my cursor, which is the stability threshold. And in this case, not only do you have the response, the asymptotic behavior, but you have the location of this existence and location of the stability threshold, telling you that this is the point of no return. And of course, after the fact, it's easy to check that when you pass that point, then there is indeed no return, and there was no way to stop the fault from moving anymore. So this is why it is very important to really spend some time on those material instabilities, understanding the behavior before we just jump into the numerics that we all want to do and run many simulations. So as Sergio was saying, basically this webinar series is all about helping people understand what is the right tool for the right job. There is no such thing as the best tool. It's all about the job at hand. And I'm hoping that everybody is really keen to build that tool belt and add as many tools as possible, because you do need more than one in order to tackle the problems that are being thrown at you. Now, on that list, if I have to put one at the very top, that would be the analytical approach. Obviously, if you can solve the equation as you have it, there is no better way to solve your problem. And if it is too hard with a pen and paper, you can always turn to a computer algebra system like Mathematica or any of those tools that you must have used. Now, apart from that, many other categories, and we heard last time from Sergio about the discrete approach, which is all about considering those discrete particles, elements, whatever you want to call them. Let's call them particles, and looking at the interaction, the forces in between them. So all nice and fine, very useful for the problems that Sergio talked about, but this is not the only family. And today I wanted to focus on the continuum approach. Now, the continuum approach is itself a whole family, right? And within this, on top of my list, I would actually put the spectral methods. I know you might have expected the finite elements, because that's what I'm supposed to talk about today. But let me just say one word about the spectral methods, because you need to know they exist in the sense that numerically, they have a lot of advantages. They have probably the best convergence rate, and that makes them a tool of choice to actually solve your continuum problem if you can use them, because they also have some drawbacks in terms of not being so flexible for the meshes and the constraints linked to the geometry. As such, this is why I'm going to talk today about the finite elements. But before that, let's mention some other families. So there exist some differential schemes like finite difference, which are particularly popular because they're extremely robust and they're quite fast. So if you have a problem that you can approximate, because this is all about basically making an approximation of your Taylor series expansion, if you can afford to do this and have a solution that you are still happy with, finite difference is probably a really good tool to get started. However, if your problem is a bit more complex, and I talked about material instabilities and the importance of considering all the physics and the couplings and the nonlinearities, then you might want to look at an integral scheme. And in terms of integral schemes, you've got things like the finite volumes or the finite elements. So for the finite elements, which is what I'm supposed to talk about today, it's all about basically getting a partition of your space to cover them with elements. So to do this, you pick those nodes, which are my black dots on the screen, but this time the nodes are no longer physical particles or physical elements of the problem at hand. They are just geometrical points that help us do a partition of the space with those elements. And I've drawn, by hand, 3 of the quads and a triangle, for example. So how does that work? As you might have imagined, it's would be a bit naive of my part to think that I can take somebody who hasn't seen this ever and fully learn finite elements in about half an hour. So instead of pretending that you're going to learn everything, I just wanted to basically cover all the aspects. So you've seen them once, you've heard the names, and you know where to look the next time if you want to dive into this method and what questions to ask. So basically, it's a special case of the Galecki method, which is a way of converting your continuous problem to a discrete one on the mesh that as just shown. And for that, there are some generic steps. The first one is to basically get your formulation. So we call it a variational formulation or weak formulation. So what does that mean? Well, it just means that you're going to start first writing your set of equations. So let's say you're dealing with a mechanical problem and you've got a momentum balance. You want to write that the divergence of stress is nil. So you put all the terms on one side, and then you have a function f of your unknowns u. So f of u equals 0. That's the most generic form we can write. This is just a normal form, but we call it the strong form by opposition to the weak form. And the weak form is just a way of saying that for mathematical trickery, the problem we're actually going to solve is not this one, but it's going to be an integral of it, where we're going to multiply our formulation by some test function and integrate this over the domain. And we want that integral to be 0. And from a mathematical perspective, you can see that, this is, you can have a non-zero function f that verifies this integral being 0. Therefore, this is a weaker form. So this is a weak form, and by opposition, this becomes a strong form, right? But these are just 9. So that's the formulation. And importantly, it's all about setting some boundary conditions. Too often people just look at the formulations thinking this is my problem, but your problem does include the boundary conditions. And I just draw your attention because you cannot neglect them. And it's important to set them properly. In particular, if you've got partial differential equations, you will need, let's say, a Dirichlet boundary condition to set the value of your unknown, for example. At that stage, you got your formulation. We now need a discretization strategy. So it starts with creating a mesh, and this is a geometrical problem. As I've just drawn on the previous slide, you want a partition of your space, and you want your elements to be as regular as possible. From that point on, we are now going to approximate our unknown u, which is the continuous value of u mathematically, with a discrete definition of u called UH, which is our numerical discrete representation that is decomposed on a basis of shape functions or triad functions. Now, those shape functions can actually be your test functions. They don't have to be. And this is just saying that you have some functions. This is basic algebra. And you have a decomposition on this basis. So you have those functions, those shape functions that are interpolary at the nodes. And for example, in a one-dimensional case, you have an element that is between -1 and 1. And then you would decompose it on 2 functions, one that is a value of 1 on one node and 0 on the other, and reciprocally for the other side. And you can see how you can write an interpolation of your function based on those 2 simple functions. Now, I've just shown an example of some other ways of doing this because there's a lot more than one. And once again, it's about using the best tool for the best job. I'm not going to tell you what it is, but you need to know that there are many ways of defining basis functions. Now, this happens to be in your reference elements. So in 1D, this is between -1 and 1, or in 2D would be on, let's say, on a perfect square, for example, or perfect triangle. Now, you have a real geometry, and therefore the next step is to get the mapping between those reference elements onto your real mesh elements. And this is the reason why I was saying that you need your mesh to be as regular as possible. You need your elements to have a good quality, meaning that you want elements that are not too elongated, not too distorted, not too skewed. Okay, you want your quads to be as close as possible as cubes, or your triangles as close as possible to equilateral triangles. And then at that stage, we can now, we have a discretization of our function u that goes into our weak form, but now we need to take the integral of it. And the last mathematical trick is to say that to compute the integral of a function of a domain, we can actually get a very close approximation by using some integration schemes, some quadrature rules, and using the value of that function at some points called integration points or Gauss points or quadrature points, multiplied by some weights. And obviously, this is much easier to just compute a few products and add them up that get a full integral. So this is something being used. And at that stage, you are now able to get your weak form with the integral of the function using your quadrature rule and using your discretization, and therefore get the whole problem expressed as a whole big vector of the unknowns, which are your degrees of freedom of your unknowns at all the nodes of your mesh. So at that stage, it becomes a new mathematical problem that you want to solve numerically. So that's the hard stage, obviously, of how to solve this, but this is for the mathematicians to do. And there are many algorithms to do. I'm just going to say a few words about this. And the last stage, finally, is about the post-processing. So in the end, you need to be able to visualize, and this needs to be written down on the list of generic steps because it's also, it can be quite time consuming. But let's talk a bit about the algorithms, really. I won't get into the mathematics, but just point out a few elements. The first one is the difference between the implicit and explicit schemes. So these are words you might have heard a few times. In case you're not very clear, let me just clarify this for you. So basically, you have a formulation, which means that you have a set of partial differential equations, and you're wondering how to solve them. Because they're mathematical and you want them discretized, there's discretization in space that we talked about with the mesh, but also with time. So you're going to break things down in time steps, and my indices represent my time steps. So time step n has been computed, and now we're wondering how to compute time step n plus 1. So after some processes, linearization and other assumptions, you can probably, for example, write a time derivative as un plus 1 minus un divided by dt, let's say. You put the dt and the un on the other side of the equation, and then you are left with an expression of your unknown at the new time step, un plus 1, as a function of all your parameters of the problem and also all the values of your unknowns at the previous steps, which you already know. In other words, everything on the right-hand side is known, and therefore there is nothing to really compute, but just simply to evaluate. So this is why it's called an explicit formulation, because you have explicitly the definition of everything. So this is extremely fast. He has huge advantages that there are no convergence issues because you are just evaluating. There is no mathematical resolution per se, but obviously you have to pay a price and you are limited to small time steps. So you've got your CFL, your current condition that prevents you from taking a time step that is too big. And in the case of mechanics, for example, you're limited by the sound wave to travel across one element, which is quite small. So basically, it is very commonly used to model the fast processes where acceleration terms matter, and it can be very efficient. On the other side, you've got the implicit formulation. So in this time, we are trying to express the value of our unknown at the time step n plus 1, un plus 1. But let's say we have a diffusion process where we have a Laplacian, which this time is derivative in space. This is derivative in space at the time n plus 1. So on the other side of the equation, we also have terms of our unknown on n plus 1. So having unknowns on all the sides, then we actually do need to properly solve the system. Okay, so this is an implicit formulation. And to solve it, you need your clever algorithms. Therefore, it is much slower. You probably / definitely will have some convergence issues. But on the positive side is that if you are able to solve it, you can solve it for much larger time steps. So these are the two approaches. And it is basically kind of necessary if you are dealing with problems like material instabilities that are highly nonlinear, that have a lot of couplings. You really want to take something that is implicit, basically. Now, for the meshing, let me specify that it is not all about the geometrical problem only, right? You need to find a partition of the space and put your nodes somewhere that your elements look good, but this is not just about the geometry, because basically the element types you're going to use are going to affect the quality of your results. So if you pick one of the commercial codes called Abacus, which is very popular, you can see that the name of the elements indicates that there's multiple choices. So the question once again is, which one should I use for my application? I'm not going to pretend I'm going to tell you the whole recipe, but just to illustrate, here's what it looks like. On this drawing, you can see 4 different cases, right? The 2 on the left-hand side are what we call linear elements. Why are they linear? Because from the mesh nodes that we have, those mesh nodes are connected by lines, by linear elements, linear segments between the nodes. So if I pick my 4 edge nodes, then I've got those 4 sides that are linear. And you can see the little crosses that are my integration points. The 2 cases on the right-hand side are what we call quadratic elements. So you can see there's some added mesh points at the middle of each of the edges. And these extra degrees of freedom allow the geometry to be more flexible and to have a quadratic interpolation or second-order interpolation between all the edges. And we can also oppose the top 2 drawings, which are called full integrations. We can see a lot of the ghost points being drawn, a lot of integration points, as opposed to the bottom 2, which are called reduced integration, which have less. So the question is, well, why do we have all these models? What is the difference, and when do we use which? So no strict rule, but if you're dealing with a mechanical problem, I would say that basically the quadratic elements provide a better precision if you have something that is simple, whatever that means, without contacts, impacts, or large distortions. And now for the full or reduced, if you can, basically the quadratic elements with the reduced integration will give you better results. So that would be the rule of thumb. Now, if you move with linear elements, because you are stuck with linear elements, then it really depends on your problem. So here's some keywords of things to look for, like hourglass modes, shear locking, volumetric locking. And let me tell you roughly what that means. Let's pick a problem of pure flexion, right? You got this rectangle and you want to flex it on the sides. Depending on which element you consider, you might have different results. So let's pick a quadratic element with reduced integration. So quadratic, which is on the right-hand side, reduced, that's this element here at the bottom. So we've got a lot of mesh nodes, but only 4 integration points. So you can see the 4 integration points on this diagram, and those lines are the isoparametric lines. And you can see that they are crossing at 90 degrees, which is what we start from. And when we flex it, those lines remain at 90 degrees because the top and bottom can bend. And this is good because this 90-degree angle translates into not having any artificial sigma 1-2 shear stress, basically. As opposed to if we are considering a linear element with full integration, which is the case on the top left corner, we also have the 4 integration points, but we no longer have the mesh points at the center of the edges. So in that case, when you flex the elements, the top and the bottom have to remain flat because they're linear. They have to be straight lines. And as a result, what you can say is that you are creating these non-90 degrees, non-orthogonal lines inside, which means that you are introducing artificially the sigma 1-2 and shear stress components. So you get a problem with the stiffness of your elements, and that is purely artificially due to the choice of your elements. So in that case, for example, if you have a linear element, you could drop to using a reduced integration element, which is this one on the bottom left-hand side. And having only 1 element, you can see that those lines will remain perpendicular, and therefore that problem disappears. So hopefully that example illustrates quite well why you need to choose carefully the type of element. Some other aspects of it are about the convergence and stabilization. So basically your convergence is at least at 2 levels, right? The first one is on the numerical convergence where you have a given mesh. So you've picked one on one of your mesh and you want to solve for it. You have some algorithms to use, and those algorithms involve some numerical tolerances. So you might have some absolute tolerances, some relative tolerances, a lot of things to fiddle with in order to get a solution that you think will be accurate enough. And in that respect, you need to be aware of the word preconditioning. This is an important aspect of it, which is one of those mathematical tricks being used to solve your problem. As I said, you have this big vector of unknowns. This is my vector X, which contains all my degrees of freedom. So if my mesh has 1 million points, and I'm solving, let's say, for temperature and for pressure, I might have 2 million degrees of freedom. So it's one big vector. And if after I linearize, I've got this equation to solve. If this is too hard to solve because it's hard to invert for A, a trick you can use is to use this preconditioner, which is a matrix P. So that P minus 1 times P gives you the identity. So it's as if you didn't do anything. And now you can look at your problem on this form. So you now have a problem in Y, where Y is nothing more than P times X. and your matrix del being A is A times P minus 1. So mathematically, you did really nothing except that having changed your problem, if you make the appropriate choice of that matrix P, that matrix AP minus 1 is much easier to invert, and same for P, and therefore you have a much easier problem that you started from. So you don't need to go too much in the mathematics, but you need to know that you will have to ask somebody who has solved a similar problem than you, which preconditioning they are using, because it will make your life much easier. And I'm sorry, it doesn't seem to be moving. Here we go. The second aspect is that you have convergence at the physical level. So this time it's about actually changing the mesh itself, right? Theoretically, the finite element method really only works when you have infinitely fine meshes. That means that if you start from a mesh that is too coarse, there is absolutely nothing that proves that you should get the exact answer. And that is something that is way too often forgotten. So please pay attention to this. You really need to do a mesh analysis. When you're solving a problem for a given mesh, you should be refining your mesh and solving the same problem again. And then looking at one aspect of your solution, could be whatever. In my case, let's say the maximum temperature. You can see that maximum temperature would evolve, for example, with the number of elements. And only when it starts converging and plateauing, do you know that you've been using enough mesh elements and that you can actually trust your numerical solution. Now, we all hope that the convergence will be really fast, but in reality, it doesn't have to be. Sometimes it's extremely slow, which is why you need to do a lot of work, including on the stabilization, so you can use more elements and solve your problem better. Same thing, this is a nice mathematical field where lots of people spend their lives working at doing this and basically canceling some of the oscillations and the checkerboard patterns that you can see, where in space you can have these seesaw patterns that are completely artificial instead of getting your proper solution, which is very smooth. So to do that, many solutions have been developed. You just need to be aware of this and look for the right keywords to find the right stabilization scheme for your problem. And I'm sorry, it seems that Zoom is taking all the resources on my laptop. I can't move. So from this, it's about getting some flexibility versus the ease of use. That's the usual story. On one hand, you can define your problem from scratch by hand, which we'll encourage everybody to do, obviously, to fully understand what it means to play with finite elements. On the other side of the spectrum, you could use a commercial software. Lots of very good ones out there. They're film specific. You have to pay the fees, but they work. And of course, there's something in between, which is what a lot of academics tend to do, including myself, which is to deal with some open source libraries and some existing frameworks so you can leverage the power of the community behind them and solve what you want. So in my case, we're using Moose, which I know some of you have been using as well, just because it is one of those very good tools out there. It is fully coupled, implicit multiphysics solver. There are lots of advantages, works on supercomputers as well, which makes it particularly useful. So features include like mesh adaptivity, where you can break down your elements. This is one of the examples where you can see that instead of running a problem on a very fine mesh, you can actually selectively define where you want to refine your mesh, and therefore saves you a lot of computational time, which is useful. And to sum up, the advantages of the finite element methods is that it is an integral scheme. Therefore, you have the higher accuracy compared to, let's say, differential schemes in some cases. You have a lot of control through your numerical tolerances and the algorithms being used, fine granularity, and it's also a deterministic approach. Last time, Sergio told us about the probabilistic approach, which also has its advantages, but sometimes you just want something that is deterministic and deal with the probabilistic level later on, which is what Florian will talk about next time. And it's particularly appropriate to handle the complex geometries, the tight couplings, nonlinearities, and some of the meshes and hybrid meshes. So you can mix and match your type of elements. You're not constrained to regular grids. And you can also mix and match the dimensionality of your elements. So here's one of the examples run by Poulet, who's working with me on faulted sedimentary basins and the flow in those basins. And you can see in here that while the rock is considered as, let's say, as a 2D medium, the faults themselves can be considered as 1D features. And then you can put the physics on those 1D features to deal with them as conduits, barriers, or a mix of both. So this is some work we've been doing recently. The problem of permeability is that when you have the permeability of a rock around a fault zone, this permeability evolves a lot. As you know, you got these damage zones where the permeability can jump by orders of magnitudes compared to the host rock. And then in the center of this damage zone, you might have a fault gouge with, let's say, clay smearing for some rocks where the permeability would drop orders of magnitudes. And then the width of these features can be quite narrow compared to the whole width of the model. Therefore, if you were to take a continuum approach, you would have to mesh everything in 3D, and therefore you would end up with a lot of very thin elements in your faults, which has a lot of drawbacks in terms of cost. Instead, if you can get rid of it and deal with a discrete approach, that might be better. If you can basically encompass all the physics of your problem, including the very low permeability fault core and the damage zones at the numerical level. So in this case, for example, you can duplicate the nodes and therefore have those nodes that are still co-located. They're just shown in here, split for visualization purposes, but you can input the constraint of the low permeability between those two nodes to handle the transversal low permeability. And then you can put lower dimensional elements on the faces of those 3D elements on either sides of the fault to handle with the high permeability damage zones, which is something that we've done to handle the sedimentary basins. So that's just an eye candy showing you an example of fault reactivation, where you got a reservoir being split on either side of a fault, and the permeability being quite high on the fault zone allows the fluid to go upwards, but not to cross over until there is a fault reactivation event that changes the transversal permeability, in which case there is an equilibration of pore pressure in the top part of the reservoir. Now, in terms of disadvantages, I mentioned the fact that it is a much higher computational cost compared to other methods like differential schemes. And also people point out that some of the relationships might not be strongly imposed. Again, nothing is perfect, but everything is addressable. So if this is a problem for you, there's plenty of work being done to ensure that you can really constrain your mass conservation in finite elements, for instance. And if you're dealing with an implicit scheme, obviously you have no insurance that it will converge. And for some people, it might be a problem. Now you just have to ask yourself whether you want a picture that might be completely wrong, or if you rather have the computer telling you, I could not converge because there is no easy solution to find. That's just a different philosophy. So the meshing is not necessarily trivial. It's easy to get something, right? You can always get a mesh, for example, using Delaunay triangulation. And the problem is that it's not necessarily of good quality. I talked about the fact that we want elements that are close to regular triangles being equilateral. This one is particularly flat, for instance. Or I talked about the importance of the choice of the elements, and that does include the geometry of them. If you have tetrahedra in 3D, you can always break them into 4 hexahedra, but then you quadruple the number of elements, plus those elements are not particularly close to a cube. So everything comes at a price. You have to make compromise. And in a few minutes I want to go quite quickly on one example of material instabilities that we solved using finite elements, and that's the problem of chemical shear zones. So very briefly, the picture you're looking at is a picture of the Glarus Thrust in Switzerland, much closer to you than to me in Australia today, where you can see a cascade of length scales. So at the top level, you see this really marked, pronounced thrust that has accommodated a displacement of more than 40 kilometers. And this happened over a fault core of the order of about 1 meter. So all the chemical and mechanical deformation occurred within this fault core, leaving the hanging wall and foot wall practically intact. And at the center of this fault core, you can see this fine line again, which is your principal slip zone of the order of a few millimeters that accommodated most of the displacement. If you take a thin section, you can see some ideas of the temporal evolution because of the overprinting of all those different shear zones. And long story short, we are proposing a model that has been published that's basically the same phenomenon happening currently underneath our feet in subduction zones and called episodic tremor and slip, where the GPS data shows that those subduction plates are not moving continuously, but they're actually stuck, they're locked for periods of time, in this case Cascadia for 14 months, and then for a very short period of about 2 weeks, they're moving by 5 millimeters. Before getting stuck for 14 months, moving in 2 weeks, 5 millimeters again. And this is the behavior that the model can capture quite well. And this model is not just in Cascadia, but it really is a heartbeat of the Earth. We can see this in various thrusts, like in the Glarus, but also in Namibia. You can see this in the northern, in Alberta. You can see the episodic tremor slip events in Canada. We've shown this in New Zealand, pictures of earthquakes in St. Andreas, in Taiwan, in Japan. So many cases are pointing to the fact that this is a phenomenon that is actually quite common in those areas of megathrust and subduction zones. The physical model, this is not the purpose of this talk, but just to tell you that it is all about the multiphysics. So you need thermal aspects, hydrological aspects, mechanical and chemical as well. Put all of this together, bit of shear heating, some fluid saturation. It's all about the chemistry and the fact that it is endothermic decomposition producing some fluids, evolution of porosity and of permeability. Put all of this together, and here's a mathematical model, which is, again, not the purpose today, but just to show you that it can be reduced to evolution of the excess pore pressure, delta P, and the temperature, T. So this is the center of the onion, and you need to do the maths to understand what that means. So it's important to do things like stability analysis to identify the different regimes that are possible and to see that you can have, stable creep. So in those diagrams, temperature pressure diagrams, every little dot at the beginning is an initial condition. That's the value of temperature and pressure at the core of the shear zone that we solve as a one-dimensional problem. And then you can see that every single of the simulation converges to the same value, which is the slow creep. And if you're wondering how we solve that problem, can you guess? It's a continuum problem. What was my first choice of tool? That is the spectral methods. All right. And you get different possible solutions. One of them is that you can have this one single event where the temperature shoots up, then the pore pressure shoots up before it converges to the same slow creep. And you can also have these limit cycles where the solution will infinitely oscillate around this limit cycle. And this is basically the oscillator. So it's very close to the problem of those Japanese bamboo sticks, which I'm sure you've all seen, where the water is feeding the bamboo. And my video is not playing because my computer is struggling, but you all imagine what's happening. Water goes in, at one point it fills in the bamboo and it just drops, empties the bamboo and it comes back up and it loops again. In this case, this is very much what's happening for the fault, where the chemistry, the shear heating is triggering the chemical reaction to go a little bit faster. That produces a bit of fluid that lubricates the fault, that makes it go faster, that raises the temperature through shear heating. You get a thermal runaway, temperature goes up. At one point, the chemical reaction produces enough fluid that the pore pressure starts going up. But because this chemical reaction is endothermic, then it sucks up the heat and the temperature diminishes while the pressure goes up to the point where the system diffuses back to its original state. And this is the result of the spectral method, showing you that you can implement all of this. You can see that the temperature and the bottom part remains very close to the 200 degrees for most of the time, except for those 2 weeks every 14 months, where there's this very quick jump. And we are capturing also the same spatial behavior that is being observed. Now, it's not about spectral methods, it's about finite elements. So where does that come into the question? It comes into the question when we do want to put back the layers of the onion, because we do want to add more complexity, more geometrical complexity, more material properties and substrate quantification. We need to put back those layers. So we need to move to something like finite elements, which is more flexible. So we've put all of this model in something called Redback, which is just one, basically an application based on mousse to implement those equations I showed you. And from that, we can observe the same behavior. So for some values of the parameter space, you can have the temperature remaining constant over time, the pore pressure as well, and therefore the full displacement that increases continuously, slowly with time. For some other values of the parameter space, we can have this one-off event with this shoot in temperature and in pore pressure, diffusing back at different time scales. And after that, which leads to a jump in the fault instantaneously at the beginning, then you've got this constant creep. And again, the more interesting part is when you get this regime, this very tiny window of the parameter space in which you can have those limit cycles and where the temperature and pore pressure will increase, will show those peaks very regularly, mathematically speaking, and leading to the fault behavior where the fault appears as locked just because it's creeping extremely slowly for 14 months. And within 2 weeks, it will jump those 5 millimeters and make this stick and slip behavior of the fault. So here's an eye candy seeing what it looks like, which is pretty much like absolutely nothing is happening for 14 months. And then you go these 2 weeks, bang, the fault moves a little bit and the temperature and pore pressure moves. So really, that was it for me, just showing you an example of this module for finite elements, why we're doing this, why it is important to focus on material instabilities. And behind this, for us, the real purpose is to try to understand better rock plasticity. The plastic regime of rocks is quite complex. And I'm sure that everybody, in case you're taking this for granted, please don't. There's still a lot of research to be done to fully understand that. So these are experiments by Oka, doing some transfer experiments on some mudstone at different confinements. And from the stress strain curves, you can see the complexity of the response. And we're quite pleased through this multiphysics to actually be able to capture this response, to try to understand why we have this response, rather than just empirically from an engineering perspective, find some parameters to match the observations, but having no predictive power when we extrapolate. And to finish, my last eye candy is basically this ability for the MOOS framework to deal with multi-scale applications, which is also quite important because all geological problems usually have this aspect of the different scales. And this is some work by Martin Messer and his PhD thesis last year, where we are inserting the problem that just mentioned of the chemical shear zone at the meter scale. So this is a meter scale line. And these are the results in red back, for example, where you can see the displacement of the fault. And this becomes the mesoscale, the medium scale, where we have this THMC oscillator. At the lower scale, at the micro scale, we can then take some CT scans and solve a Stokes problem on those macro CT scans to basically link the porosity evolution with the real permeability, rather than take an empirical relationship like Kozeny-Karman. And then at the macro scale, we can put a reservoir and put all of this together in MOOS. So that gives you my final slide, something like this, where you have this reservoir, you have a production well, and by producing from here, basically you are triggering a whole series of events. The first one is that playing with the hydraulics and effective stress, you're increasing the stress on the fault from your production. That will lead to the increase of shear heating. And as I explained before, that will just trigger the fault reactivation through the mineral decomposition. So this mineral decomposition will increase the permeability. So not only will the fault move and induce the slip, but the increase of permeability will basically allow the pore pressure to re-equilibrate between the left and the right-hand sides of the different parts of the reservoir. So the pore pressure re-equilibrates, the fault having moved relaxes the stress, and therefore the shear heating decreases, leading to the inverse chemical reaction, which is the precipitation, and getting back the fault into its locked state. So this is it in terms of application for me. And hopefully we still have a few minutes for the question. My conclusions is very simple, which is that the finite element is one powerful tool, but it's just one tool among your tool belt. So you should build a lot of other tools and understand how that works. It is useful for complex geometries and complex physical processes, and particularly for the study of material instabilities. But please be aware of the limitations and do look at all the other tools as well. So on that note, I thank you very much, and I'm open to any questions. I should probably stop sharing my screen. Yes?